Hello, for our project we'll be exploring the fascinating concepts of freefall, velocity, and acceleration using a simple yet illustrative example for our media project. Freefall is a term used to describe the motion of an object when it is falling solely under the influence of gravity. In other words, during freefall, the only force acting on the object is gravity, which pulls it downwards towards the center of the Earth. This means there is no air resistance or any other force interfering with its descent. In freefall, all objects, regardless of their mass, will accelerate at the same rate due to gravity. On Earth, this acceleration is approximately 9.81 meters per second squared. This uniform acceleration is what causes all objects to increase their velocity as they fall, making freefall a fundamental concept in understanding motion and gravity. It is important to understand how 9.81 meters per second squared is calculated as Earth's gravitational pull. In the calculation above, you can see we start out with the equation net force is equal to gravitational force experienced by the object. From here, we can convert both sides of the equation. We can say the net force is equal to mass times acceleration. As for the other side of the equation, we can say the gravitational force experienced by the object is equal to negative capital G times capital M over R squared. The variables in this equation are shown in the image on the right, and you can see capital G is the gravitational constant, capital M is the mass of the Earth, and R is the radius. From here, we can convert the equation again and form it into the new equation. Acceleration is equal to negative capital G times capital M over R squared. Next, we can substitute the known variables into our equation. The final equation we are looking at is gravity is equal to negative 6.67 times 10 to the negative 11th multiplied by 5.972 times 10 to the 24th over 6.371 times 10 to the 6th squared. The final answer is equal to 9.81 meters per second squared. This is how the force of gravity is calculated for Earth. So for our prediction, we said when a basketball is dropped from the top of CLCC, it will accelerate downwards at a constant rate due to the force of gravity. Upon impact with the ground, the ball will bounce back upwards, and its acceleration during the bounce back will remain constant. The time it takes to hit the ground, the velocity just before impact, and the subsequent motion during the bounce can be predicted using the equations of motion under gravity, assuming negligible air resistance. When watching the video, it's important to observe the motion of the basketball as it falls, and it's pretty quick when it happens. And as you can see from the short clip, the basketball was dropped from an initial velocity close to zero. The ball then gained speed until it hit the ground and proceeded to bounce back up. And by analyzing this clip and using generated graphs, we can find values like time of the fall, final velocity, and initial height, and the displacement.
The data represented in graph A shows the basketball's velocity over time during its initial drop. The y-axis represents the velocity while the x-axis represents time. From the graph, we can observe a linear relationship between the velocity and time described by the equation below. In this equation, slope is negative 8.67 meters per second squared, indicating the acceleration of the basketball. To better understand this, we can calculate the acceleration using the formula for average acceleration. Acceleration equals delta v over delta t. By substituting the values, we get what is shown below. The calculated acceleration, again, is 8.6. To evaluate the accuracy of our experimental data, we calculated the percent error, assuming the theoretical value of acceleration due to gravity is 9.8 meters per second squared. We used the formula percent yield equals actual over theoretical times 100%. The acceleration value, negative 0.865, is close to the standard of acceleration, with only 11.5% error, indicating the experiment aligns well with the theoretical expectations, though there may be some experimental deviations or approximation. The data points around 0.8 seconds show some deviation from the linear trend, which likely corresponds to the moment of impact and subsequent bounce. However, in large, the graph illustrates the vertical velocity of a ball in free fall, showing a linear relationship between velocity and time with a strong correlation. Again, the graph shows the bounce back and measured acceleration. Using the same equations before, we got an acceleration of negative 8.499 meters per second squared and a percent yield of 13.3%. This deviation from the theoretical value indicates reasonably accurate results. The negative slope indicates that the ball is accelerating downward after the bounce. The acceleration value of negative 8.499 meters per second squared is close to the standard acceleration due to gravity, indicating that the experiment aligns well with the theoretical expectations, though slight deviations could be present. The data and calculations illustrate the principle of freefall and acceleration during the bounce back, demonstrating the reliability of our experimental data. This analysis confirms that our experimental setup and measurements are consistent with the known physics of freefall and bounce back. With only a 4% discrepancy between graph A and B, it is close enough to verify the acceleration is essentially the same in both graphs. Understanding why the acceleration of the basketball remains constant during both the initial fall and the bounce back requires delving into some fundamental principles of physics. Newton's second law of motion states that the force acting on an object is equal to the mass of the object multiplied by its acceleration, expressed as F equals ma. In the context of free fall, the only force acting on the basketball is gravity, which can be represented as F equals mg, where g is the acceleration due to gravity. By equating these expressions, we get ma equals mg, implying that the acceleration a is equal to g, approximately 9.8. The principle is supported by the fact that near the Earth's surface, the gravitational field is uniformed, meaning that the acceleration due to gravity remains constant regardless of the height from which an object falls. The uniformed gravitational field ensures that any object in freefall will experience the same constant acceleration, provided no other forces act on it. Additionally, the gravitational force acting on the basketball remains constant throughout its motivation because the mass of the basketball and the acceleration due to gravity do not change. This results as a constant net force acting on the basketball, leading to a constant acceleration. In our experimental setup, we assume that air resistance is negligible. While air resistance can affect the motion of a falling object by causing it to accelerate at a rate less than 9.8, its effect on a relatively dense object, such as a basketball, over a short duration and small distance is minimal. This assumption simplifies our calculations and ensures that gravity is the primary force acting on the basketball, resulting in constant acceleration. During the initial fall, the basketball starts from rest and accelerates downward under the influence of gravity. This data from graph A shows a linear relationship between velocity and time, with a constant slope indicating a constant acceleration, approximately 8.6. This matches our expectation from Newton's second law and the assumption of uniformed gravitational field with negligible air resistance. After the basketball hits the ground, it bounces back. During the bounce, the basketball undergoes a rapid deceleration and then accelerates upward. The data from graph B shows a linear relationship between velocity and time, with a slope indicating a constant acceleration of approximately 8.4. During this bounce back, although this acceleration is slightly less than during the fall due to energy losses such as heat and sound during the impact, it still remains relatively constant, demonstrating that the forces involved are consistent and primarily gravitational. In conclusion, the consistency of the acceleration during both the initial fall and the bounce back can be attributed to several key factors. Newton's second law defines the relationship between force, mass, and acceleration, ensuring that an object in free fall will experience a constant acceleration due to gravity. The uniformed gravitational field near the Earth's surface provides consistent forces acting on the basketball, and the negligible air resistance assumption ensures that gravity remains the dominant force. These factors collectively explain why the acceleration of the basketball remains constant during its free fall and bounce back, closely matching the theoretical value of gravitational acceleration. Thank you so much for watching, and we hope you enjoyed this brief introduction to the concept of free fall.